SwayamPrabha. Digital India. Educated India.
Good morning. This is the fourth lecture on axial flow steam turbine. Contents of the lecture are reaction turbine, optimum blade speed and efficiency, multi-staging, reheat factor, and overall efficiency. The reaction turbine is one that is constructed by rows of fixed and rows of moving blades. The fixed blades act here as nozzles. Continual pressure and enthalpy drop occurs as the steam passes through stages. Here, the enthalpy drop per stage is limited. Furthermore, the construction of a reaction turbine is complicated as compared to an impulse turbine, where the surface characteristics of blades are important and it demands high accuracy. The leakage problem here to be treated with care. Efficiency is higher as compared to an impulse turbine. Moreover, here density decreases with pressure, increasing volume to accelerate the same mass flow rate, and thus the annulus cross-sectional area increases. I have indicated in figure 7 a typical construction of a reaction turbine, which consists of row of fixed blade followed by the moving blade, and a combination of fixed and moving blades is called a stage. So I have indicated here different stages, and please note that the pressure and enthalpy continuously decreases. An enthalpy drop in a single stage remains almost constant as it passes through stages, and thereby, as I have indicated here, the velocity, means the absolute velocity, increases in the fixed blade, then decreases in the moving blade. Again, in the following fixed blade, it increases and the decreases in the moving blade. Thus, this increase and decrease goes on in different stages, where the enthalpy drop in a state may be considered approximately constant. Furthermore, one should note the annulus area increases as it goes from inlet towards the exit. I have presented here the HS diagram illustrating enthalpy drop in a stage of a reaction turbine, where the state point 0 represents inlet to the stage, and the state point 2 indicates the exit from the stage, and state point 1 indicates the exit from the fixed blade. Thus, the process 1, 0, 1 indicate the actual drop of enthalpy in the fixed blade, and 1 to 2 illustrates the enthalpy drop in the moving row of blades. The corresponding isentropic enthalpy drop are indicated by 0 to 1s and 1s to 2s, where P0 be the pressure at inlet to the stage, while P2 be the pressure at exit from the stage, and P1 be the intermediate pressure at exit from the nozzle or from the fixed blade. Now, the degree of reaction can be defined as the ratio of isentropic enthalpy drop across the moving blade to the isentropic enthalpy drop across the stage. Thus, R is equal to del HB isentropic. B suffix B stands for the moving blade. Thus, del HB isentropic represents the isentropic enthalpy drop across the blade divided by del HB isentropic plus del HN isentropic. Del HN isentropic indicates the isentropic enthalpy drop across the stator or the nozzle. Here, the stator acts as a nozzle. Thus, R can be stated as H1S minus H2S divided by H0 minus H2S. So please note that R is the ratio of H1S minus H2S divided by H0 minus H2S. Now often the efficiency of rotor is same as that of the stator. Then if the efficiency of rotor is same as that of the stator, then R can be stated as actual enthalpy drop in the rotor divided by actual enthalpy drop in the stage. Thus, R is equal to H1 minus H2 divided by H0 minus H2. After definition of degree of reaction, let me discuss about 50% reaction turbine, which is called Parsons turbine. Please note that a very widely used design as 50% reactions, which is known as Parsons turbine. Here the features of the Parsons turbine are: this consists of a symmetrical rotor and stator blades. That means the inlet and exit angles are the same. Thus, the same blades can be used for the rotor and stator. Hence, ease in manufacturing, pressure and enthalpy drop is identical in the fixed blade or stator and the moving blade or the rotor. So this advantage is that we can use the same blade for the stator and rotor, where the blades are symmetrical and the pressure and entropy drops in the stator and rotor are identical. Let us continue the discussion on 50% reaction turbine. When R is equal to 0.5, the inlet and exit velocity triangle are symmetrical, and hence W2 should be equal to C1 and C2 is equal to W1, while beta 2 would be equal to alpha 1 and alpha 2 would be equal to beta 1. Hence here I have indicated the velocity triangle of a 50% reaction turbine, both the inlet and exit velocities, and they are superimposed. Thus W1 plus U is equal to C1, and beta 1 and alpha 1 be the relative and absolute angle, while W2 plus U would be equal to C2, and I have also indicated beta 2 and alpha 2. Now, since it's a reaction turbine, the pressure decreases within the rotor, thereby W2 will be greater than W1 because the flow has accelerated. However, in a 50% reaction turbine, both the triangles are symmetrical, hence W2 should be equal to C1 and W1 would be equal to C2. Furthermore, beta 1 would be equal to alpha 1 and beta 2 would be equal to alpha 2. Thus, these two triangle inlet and exit are the mirror image of each other. After explaining the velocity triangle of a 50% reaction turbine, I can say now the energy input E per unit mass can be given by the energy object plus pressure energy gained by the rotor. Again, I can say the energy input E per unit mass flow rate can be stated as energy object, which is coming from the nozzle, plus pressure energy gain because of expansion of fluid with the rotor. Thus, E is equal to C1 square by 2 plus half W2 square minus W1 square. Now, W2 equal to C1, hence I can write E equal to C1 square by 2 plus C1 square minus W1 square by 2. This would be equal to C1 square minus W1 square by 2. Thereby, E can be given as C1 square minus W1 square by 2. Now, from the inlet velocity triangle to the rotor, I can write W1 square is equal to C1 square plus U square minus twice C1 U into cos alpha 1. Thus, putting the value of W1 square in the earlier equation, I can write E is equal to C1 square minus C1 square plus U square minus twice C1 into U into cos alpha 1 divided by 2, which becomes C1 square minus U square plus twice C1 U cos alpha 1 divided by 2. Now, the work done per unit mass flow rate W can be given by U into del C theta. Since the velocity triangle are symmetrical, del C theta can be given by twice C theta 1 minus U, that is twice C1 cos alpha 1 minus U. Hence W is equal to U within bracket twice C1 cos alpha 1 minus U. So I have got the expression for E. I have got the expression for W. Thus the blade efficiency is expressed as eta B is equal to W by E, which is equal to twice U within the bracket twice C1 cos alpha 1 minus U divided by C1 squared minus U squared plus twice C1 U into cos alpha 1. Thus, I have got the expression for blade efficiency of a 50% reaction turbine. Let us consider the speed ratio rho as U by C1. Now the blade efficiency can be expressed as eta B is equal to twice rho within the bracket twice cos alpha 1 minus rho divided by 1 minus rho squared plus twice rho into cos alpha 1. For a particular blade design, alpha 1 can be treated as constant, and thus blade efficiency is a function of rho. Hence, for maximum blade efficiency, I can say d eta b by d rho is equal to 0, which yields 4 cos alpha 1 minus 4 rho within the bracket 1 minus rho squared plus twice rho into cos alpha 1 minus within the bracket twice rho within bracket twice cos alpha 1 minus rho again within the bracket minus 2 rho plus twice cos alpha 1 divided by 1 minus rho squared plus twice rho cos alpha 1 whole to the power square is equal to 0. Please check the expression, and this will lead to rho optimum, that is equal to U by C1 optimum would be equal to cos alpha 1. So optimum blade speed ratio for a 50% reaction turbine would be equal to cos alpha 1. I have already indicated that alpha 1 is recommended in between 15 to 25 degree. Thus, for a 50% reaction turbine, the blade speed U would be close to C1, while for an impulse turbine, blade speed would be close to half of C1. Further, eta B maximum would be equal to twice cos square alpha 1 divided by 1 plus cos squared alpha 1, which illustrates that the efficiency of a reaction turbine is more than that of the impulse turbine. Moreover, under this condition, the absolute velocity leaving the stage would be axial, and the velocity triangle at optimum condition has been indicated in figure 10, where alpha 2 and beta 1 would be equal to 90 degree. The C2 would be axial, as I have indicated here. If C2 is axial, being a 50%, C2 must be equal to W1, and W1 also would be equal to axial. Thus, for optimum blade speed of a 50% reaction turbine, U by C1 is equal to cos alpha 1, and thus the energy transfer would be E is equal to U into del C theta. Now here del C theta would be equal to U, then E becomes U squared. Now I'd like to remind you in brief that the maximum blade efficiency of an impulse turbine is eta B max is equal to cos squared alpha 1, while the maximum efficiency of a 50% reaction turbine is eta B max is equal to twice cos squared alpha 1 divided by 1 plus cos squared alpha 1. Hence, the blade efficiency is higher for a reaction turbine. However, the energy input per stage is less, and thus a reaction turbine requires more stages. I have compared here the performance of a reaction versus impulse turbine. Please note that the efficiency of a reaction turbine is higher than that of the impulse turbine, where the optimum blade speed ratio for the reaction turbine is given by cos alpha 1, while the optimum blade speed ratio for the impulse turbine is given by cos alpha 1 by 2. So far I have discussed about a single stage reaction turbine, particularly 50% reaction turbine, its efficiency and the optimum blade speed. Now I'll discuss about multi-staging, read factor, and overall efficiency of a multi-stage turbine. I'll initiate an important discussion on multi-stage. Here I'll define the overall turbine efficiency and the read factor. The thermodynamic effect on a turbine and its efficiency can be best understood by considering enthalpy drop across multi-stages between the state point 1 and 2 as shown in the figure. In the figure 12, I have illustrated the enthalpy drop across a multi-stage steam turbine where the state point of fluid at inlet to the turbine is indicated by the Roman numerics 1 and at the exit of the turbine is denoted by the Roman numeric 2. So here 1 and 2 indicate the overall enthalpy drop across 4 stages here. Now P1 be the inlet pressure and P2 indicates the exit pressure from the multi-stage turbine, and P2, P3, P4 indicate the intermediate pressure. So I can now know the pressure drop in each stage. Thus, the total expansion is divided here into 4 stages of the same pressure ratio and the stage efficiency. So this is a very important consideration where I am considering that the pressure ratio of each stage be almost same and thus the stage efficiency. If the pressure ratio of each stage is same, then I can say P1 by P2 must be equal to P2 by P3, P3 by P4, and then P4 by P2, that is Roman 2. So what I like to say here, the pressure ratio of each stage are the same. With respect to a multi-stage steam turbine, as indicated in figure 12, let me consider the overall efficiency of the multi-stage turbine is eta 0. Then eta 0 can be expressed as the actual enthalpy drop during the process 1-2 divided by isentropic enthalpy drop during the process 1-2s, which can also be expressed as WA divided by WIS, where WA be the actual work and WIS be the isentropic work during the expansion process 1-2, So this is 1 to 2s be the isentropic enthalpy drop, while this is the actual 1 to 2 represents the actual enthalpy drop. So I have indicated here eta 0 is equal to del H 1 2 divided by del H 1 2s. I have already discussed about reheat factor while presenting axial flow compression. Now let me explain again. Now here I have taken as an example 4 stages where the pressure ratio and stage efficiency of each are the same. Now Roman 1 and 2 represent the inlet and exit of the multi-stage turbine, while 1, 2, 2, 3, 3, 4 and finally 4, 2 represents the expansion in each stages. Therefore, I can define actual and isentropic drop of enthalpy of every stage. Thereby, reheat factor is defined here as cumulative isentropic enthalpy drop divided by isentropic overall enthalpy drop. Hence, if I represent reheat factor by RF, then RF is equal to del H 1 2s plus del H 2 3s plus del H 3 4s plus del H 4 5s. This is the cumulative drop, isentropic enthalpy drop divided by del H 1 2s, that is overall isentropic enthalpy drop. Hence, reheat factor is given by sigma del Hs, where del Hs is the enthalpy drop of the stage. Again, let me repeat. Del Hs represents the enthalpy drop of stage. So sigma del H is divided by del H1 2s. Del H1 2s represents the isentropic overall enthalpy drop. Thus, here I have defined reheat factor related to multi-stage steam turbine. Now let us consider eta S be the mean stage efficiency, which remains constant for all the stages. Now come to the figure. Here, if I consider the second stage, so the actual enthalpy drop will be given by del H 2 3, whereas isentropic enthalpy drop will be given by del H 2 3s. So please note 2s, 3s, 4s and 5s. These are all the points where the expansion is considered isentropic. So thus, stage efficiency can be defined as the ratio of actual enthalpy drop divided by isentropic enthalpy drop for the stage. Thus, I can write eta S is equal to del H 1 2 divided by del H 1 2s. That also be equal to del H 2 3 divided by del H 2 3s, and thus finally del H 4 2 divided by del H 4 5s. What I like to mean here, all stage efficiency I have considered same. Now, if I consider all stages efficiency are same, then I can write eta S is equal to del H12 plus del H23 plus del H34 plus del H42 and divide by add all these things, that means del H12S plus del H23S plus del H34S plus del H45S. That is, it leads to del H12, that means actual enthalpy drop during the expansion process 1 and 2 divided by sigma del H, that is cumulative isentropic enthalpy drop. Hence, I have got that expression of eta S, which is again del H12 divided by sigma del Hs, where del Hs represents the stage enthalpy drop, isentropic enthalpy drop. Now, we know eta 0 is equal to del H12, that is actual enthalpy drop from inlet to the exit of the turbine, divided by del H12S, isentropic enthalpy drop. That can be written as sigma del Hs divided by del H12S into del H12 divided by sigma del Hs. Some manipulation I did. If you do that, this is nothing but reheat factor and this is stage efficiency. Thus, I can easily prove that overall efficiency is equal to reheat factor into small stage efficiency. The average value of reheat factor is 1.03 to 1.04. Thus, the overall efficiency of a turbine is greater than the individual stage efficiency. This is because the aerodynamic loss can be partially recovered in case of a turbine. Further, the turbine is rotated at a constant speed for different load. This is done by governing or controlling of steam turbine. There are three ways of governing, namely throttle governing, nozzle governing, and bypass governing. A combination of these three is used in practical situations. In this lecture, I have discussed about reaction turbine, multi-staging, and reheat factor. Thank you for listening.